scatter-to-gather transformation. And so this is basically a way of doing a particular kind of common, really sort of like in HPC, so high performance computing computation pattern that we often see in CPU code. And you want to do this kind of transformation when we're moving to GPU code. And there's an example that's about half this lecture that I think will make that a little more clear. But basically, the gist is that it's a very common pattern where you have some series of inputs and some series of outputs, and every input affects every output of this block. And so basically the way we might express this in C is, we have this nested loop where our outer loop goes over the inputs, and then our inner loop goes over the outputs. And in that way, we cover every input, do some computation on the input, and affect every output. And so this is a fairly common thing. We can think of some sort of different cases for this. So maybe say if there was only one output, that might, for example, be the reduction that we did in 408, right? Or maybe if not all inputs affected every output. So you can imagine there's like a window of inputs that affect each output. So there's some differences here, and we're going to actually talk about. So we already talked about the case where there's one output, how you do that in 408. And we'll come back to that at the very end. In the case where you have a window of inputs affecting each output, there's a technique called binning, which we will cover at a different lecture. So for this particular case, we're really just talking about this sort of generic all inputs affect all outputs. And so, this is kind of what I was just talking about, but very generically, right? Let's say we have M inputs and N outputs. And this example is maybe like an X-ray scan or some kind of three-dimensional scan of something. And so, for example, we might have it would be common in this computation pattern to have some set of inputs that seem somewhat irregular. So for example, these input points, if we look at them in a Cartesian grid, they don't necessarily fall on like nice grid points. But maybe our output is regularized in some way. So our output does have some nice regular structure that we want to take advantage of in GPU. But basically the computation pattern is that we loop across all of our inputs and all of our outputs, and then sort of generally each output element is some function that depends on all of the input elements and transforms them based on the input and output position, right? So this covers like any arbitrary generic transformation of the input elements based on their position and the position of the output element, right? So that's what we're trying to convey here. And this function can be quite complicated, right? But we're just pretending it's just a function. And so, of course, the complexity of this is, the number of input points multiplied by the number of output points, right? Because we cover all of them. For each output point, we cover all the input points. For each input point, we affect all the output points. Wrong way now. And so, sort of the simplest way, or maybe the most obvious way to parallelize this, is to just parallelize across the inputs. So for example, we would assign one thread to every input element, and each of those threads would take a look at its input element and affect all of the output elements appropriately. Okay, so that's what this picture is showing here. So we'll have, as many threads as input elements, or in CUDA, probably what we would do is we would have some fixed grid size, and our entire grid would move over all the inputs, affecting all of the outputs. And so this is called a scatter parallelization. And the reason it's called a scatter is you can think of it, we're sort of thinking of it from the thread's perspective. So I'm a thread, I take my input, and I affect all the outputs. I just throw my input to all of the outputs. I scatter it across all the outputs. And so the transformation that we're trying to do, and so the problem with this, maybe you can immediately see, is that it's sort of a similar problem. Well, the problem is that these threads, right, in general, any two threads in our grid, there's no order in which they execute, right? So they can be executing one after the other, or they can be executing at the same time. And the problem is that both these threads are executing at the same time, trying to access the same output element, we'll have a race condition, and our result in this output might be wrong, right? Because to modify one of these output elements in memory, a thread will load the value into a register, modify the value internally in the register, and then store it back to the memory. And if two threads both load this output element into their registers, both try to add 1 to it, and both store it back, we're going to have the wrong answer here because they'll both have loaded the original value, both added 1 to it, both placed the original value plus 1 back in, and we'll get the original value plus 1 instead of the original value plus 2, right? And so we sort of face this problem in 408, and there's one easy solution to doing this. Oh, and so of course we don't have this problem on the CPU, right? Or in our sequential implementation, because we're only looking at inputs and outputs kind of one at a time. And so we get to sequentially and correctly avoid the race conditions by not doing anything in parallel. So the reason that it's very slow is because the easy fix to this is just do all the modification operations atomically to all the outputs, right? So every thread's going to compute what modification it wants to do to an output based on its input, and then just atomically add that, or atomically exchange, or whatever the right operation is. And so if there's a large number of threads all trying to collaborate into a single output, there will be a lot of conflicts here, right? So if we only have 2 threads, maybe it's not so much of a problem, but what we're going to have is we're going to have maybe as many threads as we have inputs. So there could be a lot of contention for each output, and then the execution will be slow. It'll be serialized, so we lose a lot of the benefit that we got from parallelizing. Right. So we serialize updates to output 0, we serialize updates to output 1, and so on. So an alternative approach to parallelizing this is called gather, and that's where we, instead of assigning a thread to each input, we assign a thread to each output. Right? So we have the CUDA threads, and we get to do with them what we choose. It's not like CUDA tells us that we have to do it. 1 thread per input or 1 thread per output. And so this is a little different. Each thread owns one of these outputs essentially, and it looks at all of the inputs, and then computes the correct output value and just stores it there. And the reason that we don't have a race condition here is because we're not doing any modification of the input, right? We're just reading it. So we don't need to do any atomic operations or anything like that. And so here, the amount of parallelism that we have available is sort of controlled by the number of outputs, right? We can't really, if we have more threads than outputs, we're either not going to be using some of our threads, or we're kind of back where we started, where somehow we're going to have to coordinate between multiple threads working on each output. And in the previous case, we have the number of threads that we can have is kind of limited by the number of inputs. So that's a trade-off. If the inputs or outputs are very different sizes, that might override the question of whether scatter or gather is faster or slower. Just because if you only have 2 outputs, you're probably not only going to want to parallelize by 2. You might parallelize across the inputs and just eat the cost of the serialization at the end or something like that. Great. So gather can be fast for it fixes the problem that we had with scatter being slow. So first of all, there's no serialization. But even better is that we can take advantage of the fact that many of the threads are accessing the same elements of the input at the same time. Right? And so like we talked about some in 408, one of the main things that we're really trying to do when we're thinking about algorithms for CUDA is we're trying to capture data reuse. So we don't have to keep accessing global memory. And just the nature of the gather pattern makes that very easy to do. Because, for example, thread 1 and thread 2 can read the first input at the same time, right? And then they can read the second input at the same time, read the third input at the same time. And so you can imagine that maybe thread 1 and thread 2, if they're in the same warp, if they're both reading input 0, then the chip only has to go to the DRAM once to get input 0 for those 2 threads. It only has to issue 1 load, and then it can serve them to both threads in the warp. Or we could take a chunk of our inputs and explicitly move it to shared memory and then have the threads access it from there. So sometimes the architecture will automatically help us. Maybe it'll get cached. So when one of these threads accesses it, the next time another thread accesses it in a different work, it'll still be in the cache. So maybe the architecture helps us, or maybe we can explicitly capture that locality of the shared memory. Either way. So yeah, in addition to not having to do serialization anymore, we can also capture this locality of the input, which is just sort of sitting there for us. And again, every thread is updating its own output element, so there's no need to coordinate the writes. And so, I mean, this sort of raises the question of why you would even ever use it. And basically the answer is that two things. One of the things I already mentioned is that in a lot of times you won't have every input affect every output. And so one reason for that might be that, say we're trying to model, I don't know, the universe, right? And every point of mass in the universe exerts a gravitational pull on every other point of mass in the universe, right? So we can imagine that we might want to compute the sort of gravitational field of the whole universe from each of these points. But you know, points that are very far away are essentially going to not influence me, right? So instead of going over and computing those points and discovering that their effect on me is 0, I just won't even bother computing them. I'll just approximate it to 0. So maybe we'll take advantage of some physical property of our system that says, you know, far away things have no effect on us, so we won't bother computing it. So that might mean an input element does not affect every single output element. And another reason that this is done is sometimes because the output tends to be a lot more regular than the input. And so it's kind of easier to, I don't really know if I buy this. I would say really it's this first one, and I would say the second one is often that the CPU code is written in a scatter style. So it's just easy to directly take that code from like a software engineering perspective and write a CUDA implementation that's more similar. It's easier to maintain. Though this is true, it's not really clear to me why that would affect scatter rather than that. Okay. So, okay. So, because the output elements are regular, it's easier to calculate which output elements are affected by an input element than vice versa. So maybe I can make this a little more clear. So say, we can go back to our universe example. So say I'm trying to model a three-dimensional space, the gravitational potential in the three-dimensional space, okay? And I basically have a bunch of, you know, point masses floating around in here, right? And so my input is really an array of point masses and, you know, maybe 3 other arrays of their x, y, and z coordinates. And my output is a regular grid, right, of points in the field. And so it's easy for me to look at an input element and say, you know, based on its x, y, z coordinate, if it falls here, it affects these output grid points, right? Maybe it's just the floor of x plus some distance and the floor of y plus some distance, right? It's easy to go from this irregular data to find a regular position. But if I just go and I say, what input points affect this cube in my space? If this data is irregular, the only way I can figure out which input points affect this is by checking all of them. So I hope, this is a simple example, but I hope it's kind of convinced you that it's easier to go from irregular to regular than vice versa. So, yeah, so if it's scatter, so it's easy to write this in sort of a scatter style where I look at my input and then I know where to affect all the outputs. It's easier to write that than the other way around. And maybe computationally less expensive as well in sequential. Great. So basically, to do a gather parallelization, we need to solve that problem. Somehow regularize the input elements so that it's not this huge expensive task to figure out which inputs affect which outputs. But remember that we'll talk about that, how to do that in the future. For now, we know all inputs affect all outputs, so we don't have that problem. So the example that we're going to do for the rest of this class is to sort of motivate this transformation is not this sort of gravity field point mass example, but it's quite similar. This was some code that our research group worked with before I joined it. But it's a biomolecular simulation where instead of computing a gravitational potential field, you're computing an electrical potential field. And I guess the idea is that because of the structure of the inputs, I guess you're trying to figure out how particular ions bond with biological structures. And the way they do that is they try to bond in like the lowest possible energy state. And so you want to compute this energy field, and then you put the ions in the places that make it the lowest possible energy states. So it's quite similar to this example. Basically what we're trying to do is look at a bunch of inputs, sort of irregularly placed inputs. They all have an effect on this three-dimensional regular field. It's just that it's an electrical field and charged particles instead of a gravity field and massive particles. And that's the expensive part of the computation. And so I guess this was done, some modeling work that was done back in the institute. So great forward. Okay, so this is the process of the application. So we're calculating this electrostatic potential map based on the contributions from these charged particles. And so, right, this is sort of the picture I just drew over here, right? We have some irregularly spaced atoms. They probably have a charge and a location associated with them. And then we have this regular output points where we're trying to compute these electrostatic field to approximate, the electrostatic field in space. And then I guess there's this ion placement strategy to figure out where the ions go when they're interacting with the biological structures to model the biology in question. But that's not really the focus of what we're doing. Our focus is really on this part, in the scatter together ramifications. So okay, so this is, I guess, called the direct Coulomb summation algorithm. But basically, it's this process that I already described. We go through all of the inputs. Each input affects all of the lattice points based on its charge and its distance from them. And you basically just sum up all of the charges and the distances for each output point to compute this electrostatic potential. And then if you want, you can make approximations, like if my atom is very far away from part of my electrostatic potential map, I will assume, right, if it's far away, we're dividing by a large number, and so we can just assume that that's 0. And that gives you some loss of accuracy, right, because it's not 0. But the nice thing is that you don't have to compute all m inputs for all your n outputs, so it's faster. But right, we're going to talk about that later in binning. It's cool. Okay. So, right, just to reiterate, for every lattice point, we look at all of the atoms and add up their effect on the potential, which is their charge, which can be positive or negative, and the distance that they are. And so I guess these are some of the parameters of the example, but these are, in any problem that's like this, these are the kinds of parameters that are going to define the problem, right? So you have the extent of your grid, a pointer to the data that, okay. So you have a pointer to the data that represents your potential map, right? And that's regular, so you can directly compute sort of the actual physical space based on the index into that potential map, right? So I have some physical space in question, I don't know, maybe it's 10 angstroms by 10 angstroms by 10 angstroms. And if I divided 1,000 each way, I can compute my physical location in that space just based off the index in the space. That's what we mean by regular. Right, the spacing in that grid, the grid and the spacing of that grid determines that regularity. And I guess the way this is implemented is that the 3D space is divided into sort of flat slices. So each of those slices has a z coordinate. So when our kernel is executing, we're really just doing a 2D chunk of that. So when we're computing that 2D chunk, we need to know which 2D slice it is. And then we have this array of atoms, right? And like I mentioned, it's really an array of x, y, and z coordinates in charge. So the atoms are not regular. The atoms are just charge in their locations. And of course the numbers. And so right here's our function signature. This, but just to make this, I guess there's a little picture here just to make this a little more clear. So the grid here is in blue, then we have the dimensions of the grid or the extent of the grid, the spacing of the grid, so the size of one of these cells, and then the atoms, their position in charge, and number of them. So the sequential C version is pretty straightforward, right? Basically it's a set of nested loops because we need to loop over all of the atoms and all of the grid points. So we should see, except it's a two-dimensional slice. So we loop over x here, y here, and then all of the atoms, right? So there's our 3 loops. And you can see that it's input oriented, so this is the scatter. And what we do in this sequential loop is anything that's so-called invariant in the lower loops, we pre-compute. And so this is probably a common thing that you do, even if you don't really know what it was called. These are loop invariants. So for example, dz, right, we're in a particular z slice. We need to know how far we are from any particular atom, but that's not going to change. We're always in the same z slice when we're looking here. So no matter which x and y output coordinate we're looking at, it's always the same z coordinate. So we don't need to recompute that every time. And so likewise, as we're going through x coordinates, the y coordinate is always the same. So you can see we don't have to recompute these every time. But anyway, so it's this input-oriented loop over all the atoms. And so I guess the way this array is structured is that it's packed so that each atom, it's really an array of sort of these structures. So it's an array of charge x, y, z, charge x, y, z. Right? So, for example, the charge is the atom you're at plus 30 or something, or maybe it's x, y, z charge. But it's packed like that. So you pre-calculate these sort of invariant quantities, and then we do the same in the y and the x direction. And so this code is pretty simple. Pretty simple to sort of wrap your head around. But here we go, we've computed the charge, and we just divide it by the distance, right, and add it to our regular output offset. So again, it's input oriented. For every input atom, we're calculating its contribution to all points in the output potential map. And this regular point that I was making before, we just have indices and model physical coordinates. You can directly compute them. And then the input is irregular. It's regular in the sense that it's stored in an array, but it's irregular in the sense that its location in the array has no correlation with its location in physical space or the modeled space, right? So the nice thing about the sequential algorithm is that we're doing sort of the minimal possible amount of computation, right? So this is getting to that efficiency component. We talked about that a little bit in 408 when we were talking about like the prefix scan, I think. But there's sometimes when you have a parallel algorithm, you end up doing more work than the sequential algorithm, right? So here, we do the minimal possible calculations on the charges, the distances, the coordinates, to come up with the final answer. And so I guess one question is, why are these inputs irregular and the outputs regular? And I mean, I think we've kind of belabored this point enough, but basically, we're modeling the electrostatic potential value at all of the points in the space. Ultimately, that's what we want, but really when we're computing it, we have to do it with some resolution. And so we choose to do it at regular points. I guess we wouldn't have to, but we choose to because it's easier. But the atoms come from modeled molecular structures that don't necessarily have a regular pattern. Their atoms are placed there for reasons that we maybe don't entirely understand, or that's why we're doing this reason. So it's sort of a constraint on our problem that the inputs are random. And so this sort of overview of the overall code is probably very familiar to you, right? But first, we allocate memory on the host CPU and initialize it correctly. We allocate the memory on the GPU. Okay, so I guess there's some preprocessing or initialization work, but for all of the 2D slices, we copy that slice onto the GPU. We loop over all of the atoms. Maybe all of our atoms don't fit on the GPU, so we'll just do a few of them at a time. But we'll move, so over all the potential slices, over all the atoms, we run the CUDA kernel, looking at a piece of atom, a chunk of, or a set of atoms, and how it affects all the different potentials of the potential map. And once we've done that for all of the atoms, we'll have the result for the entire potential map. Copy the map back to the host, and then we're done. Right. So this is pretty familiar to people who have written CUDA code before. And so, sort of the natural way to parallelize this in CUDA is instead of looping over all the atoms, right? This is the scatter parallelization. Instead of looping over all the atoms, we just have one thread operate on each atom. And so this is exactly the scatter parallelization, because each thread looks at its atom, it computes how that atom affects the potential at every grid point, and updates every grid point accordingly. And if we have every thread doing that for every atom, then we've achieved the correct result. So basically it looks exactly like the CPU version, except the outer loop is gone, and it's replaced by, checking what thread ID we are. And so you may have kind of had this experience a little bit when you were doing 408. Maybe you wrote some code. The first thing you did in your CPU implementation was, you can sort of debug a GPU code sometimes by just taking the kernel, replacing the kernel call with like a for loop over a thread ID. I don't know if you've ever tried that, but right, the idea is that all of the threads are parallel and independent. So you can just put that inside a loop on the CPU, and maybe if it's easier to debug it that way, you can do that. So that's essentially what we do. We just, instead of looping over all the threads, we do a kernel, or looping over all the atoms, we do a kernel launch based on the number of atoms. And so each thread is a loop iteration on the atoms. And then we check the number of atoms to figure out how many threads to launch. In general, this is a bit of a digression, but I'm actually kind of opposed to this approach, although it's really what we do commonly in 408, right? So if you think back to, say, the vector add, it would be common to say, well, look at how many elements we have in our vector, divided by the grid size, or the block size, right, to figure out how many blocks to launch. Typically, what you might consider doing instead is always launching a fixed size grid, and then having that grid loop over all of the inputs. So it's common to sort of pop off your kernel code with, if the thread ID is less than n, do it, right? Otherwise, do nothing. What you can kind of replace that with is a for loop. It's basically, for I equals 0, I is less than, or not I equals 0, before I equals the grid ID, the thread ID within the grid, I is less than n, and then increment I by the grid size. And then, if your input becomes larger in any dimension than CUDA supports for a grid size, your code will support. So it's kind of just a little digression, but this totally works too. So this is the kernel, right? So all we've done basically is we've taken away that outer loop over all the atoms, but otherwise the code is essentially the same. Okay, so we just check now what thread ID we are to figure out which atom we are. So that's this block ID times block dim plus thread ID. Right? And so why do we say this is slow? First of all, this isn't even correct. right? Because any atom could be updating any grid point at any time, because all of the threads just execute whenever they want. So we have to do this as an atomic. So basically, this add needs to be an atomic add. Luckily, CUDA has some atomic operations for us. But basically, these are functions. They're expressed as functions in your source code, but really they map to single assembly instructions. And basically what you do is you provide an address, so a pointer to a memory location, and a value that you want to atomically increment it by. And CUDA will ensure that this the load, modify, store happens atomically. It can't be split up, right? That's what atomically means. It's one indivisible unit. So I think that's Greek. And I think atoms were originally called atoms because it was thought that they were not dividable, not divisible, although that, of course, turned out not to be true. But anyway, this is indivisible. So, borrowing some kind of hardware book, I guess. So basically, CUDA provides atomic operations for all kinds of data types now. I don't know exactly what they are on our systems, but it's at least, so sort of the hardest operations to provide atomic data points for are large floating point operands, because they require a lot of hardware to do the additions. And I think our GPUs have support for 64-bit floating point numbers, so you can do like any integer and any floating point numbers that you want. So you don't really have to worry about types. But back in the day, when we were working on this problem, there were some pretty tough restrictions on what kind of operations atomic support you could do. Oh, so I guess this gets to that a little bit. So they didn't even have floating point atomics at all in early GPUs, but now we have floating point. We have atomics on everything. So, but basically, you can look up in the programming guide. But essentially, the atomic that it chooses is going to be based on the types of the pointers that you give it. So sometimes you'll see an error if you try to use this, where you'll like give it a float, and depending on like what compiler flags you have turned on, you'll like give it one type, and then you'll put like just constant 1 in there, and it'll say, I don't know how to do an atomic add between a double and an integer. And so you can just like, explicitly make this a double, and that will stop whining. Okay, so we talked about this a little bit, but I don't want to undersell the scatter kernel, right? It is slow, because you have to do atomics, but it has this really strong benefit, which is that it's the same as the CPU version. So if you inevitably find a bug in your code, it's easy to fix in both places. Or possibly you don't even end up writing 2 pieces of code, you just do some like macros or something to have the C and CUDA version be the same, right? And I can't emphasize enough how valuable that is. We have active research projects in our group trying to make it so that people can write one piece of code that works well on CPUs and multi-socket CPUs and GPUs. And it's a really thorny problem because for reasons like this. Like, if we could automatically always do a scatter-to-gather transformation, that would be great. But it's tough to sort of do that automatically, which is why we're teaching in the class. So, so good for software engineering and code maintenance. There's really not very many places in the world where it's worth paying someone to really, really, really optimize a piece of code. Like one of the few places where that's true is like supercomputing. But most of the world is just like, okay, get it working and make it easy to maintain and we'll move on. But also the nice thing is that it preserves this computation efficiency, right? So that's a good thing. But the problem is that because of the cost in our architecture of atomic operations, it's slow. So now let's think about the output-oriented or gather version. So this is the C code for the gather version. And it's labeled as slow. And the reason that it's slow is because, remember how we were trying to, in the other code, we got to do this thing where we would like pre-compute some of these values that were invariant in the loops. In the output code, oriented code, we don't have as much opportunity to do that. But first, let's notice that this is output oriented. So we're looping over y, or we're looping over y and then x and then the number of atoms. Right? So instead of looping over the number of atoms and then all of our outputs, we're computing. Yeah, we're writing to every iteration writes to a single output, but it accumulates the effect of all of the atoms before it writes to it. So this is the problem, right? Because there's many. Right, for many of these x's, this y is the same. But in this code, we have to compute this inside the innermost loop. So this is why it's slower. So I guess some pros of this is that that code was a little bit shorter. I suppose that's true. And the reason that was shorter, I mean, this seems a little unfair to me. The reason that it's shorter, like the original code could have also been short if we were not willing to pre-compute some of those values. We had a few lines of code to do that, to compute the invariance. There's also fewer accesses to the output array, which potentially is good depending on how expensive it is for you to store to memory. But the cons is that it's less efficient. We have to read this irregular atom array more often. And basically, because of the number of calculations we do, it's much slower than the other. So this is how we're going to decompose this problem for CUDA. It's pretty simple, right? It's not really too shocking, but basically we have this two-dimensional space in blue that we're trying to compute static potential in, and we're going to assign one thread to each location in that grid. And because we have to create the graded granularity of thread blocks, there's going to be some threads that are doing it. So nothing you haven't seen before, I think. Potential. Sure. So this is just the CUDA version of this scatter group. So we just, instead of having those outer loops over the x and y of the grid point, we have one thread per grid point. So we've taken those two outer loops and turned that into the two-dimensional CUDA grid. So that's that top part. And then we have this same inner loop where for every atom, we compute the distance that the grid point is from that atom, and then use that to compute, the effect on the electrostatic. So one thing I guess to note here is that all of the threads access all of the atoms in the same order. So that means, most importantly, that means that every thread in a particular warp is accessing all the atoms at the same time. Or all of, atom 0 and then atom 1, all the threads in the warp. So you get, it's very similar to like coalescing. You only have to get one load to get the data to all the threads. One right to the energy grid at the end of the loop. So we only have one thread per grid element, and there's only one write to the grid in each thread. Although they're reading from the atoms. So dz times dz can be pre-calculated. So you'll notice that z is an input, and then every thread computes z squared. dz. Because we're working on a 2D slice, we can go ahead and compute this dz squared value for all these atoms before we launch the kernel. And that prevents everyone here from needing to compute this. Yeah?
Why do you have that addition over here? Because you're doing times over that, right?
Where?
Yeah.
Here?
Yeah.
Oh, so, right, that's a good question. So this kind of, so you should just be able to say equals here. I guess this would work if this was initialized to 0. That's a good question. Good eye. And so this would prevent, this would reduce some of that redundant computation. So does that make sense? All of the atoms can compute. We don't need to be in the CUDA kernel. We know what Z component we're in the CUDA kernel before any of the threads launch. They're all the same. So for all the atoms, we can compute this DZ component before we even launch the kernel. We do that on the CPU, so maybe you think that's slower. The plus side is that we don't have to compute it all in here, and we're computing it many more times in here. We're computing it X by Y times in here, as opposed to just once outside. So, trade-off. No serialization due to atomic operations, so that's good. So, because we did this gather to scatter, we don't get the compute efficiency of the sequential algorithm in the fast parallel algorithm. I guess we're going to talk about this a little bit more later in the course. But I think this is just another one of those cases we're getting the fast parallel algorithm because of some of the, fundamentally the reason that we're jumping through all these hoops is because when we do it in parallel, right, how do we do it? When we tried to do it in parallel with the scatter approach, we discovered we had to do atomic operations. And atomic operations are slow because of our architecture. If we somehow magically had fast atomic operations, we'd be like, great, right? So, this is what I was talking about yesterday, where a lot of these choices that we end up making are really driven by the characteristics of the architecture, not really necessarily something intrinsic about the problem. So there's this intrinsic about the problem where we end up doing redundant computations sometimes because of a particular algorithm that we pick. But the algorithm that we pick is also motivated by the constraints and properties of the hardware. So just take it back out to the big picture there. So this is some results on from this case study. And so these are GPU architectures, and so Maxwell is not the newest one anymore. Since then they've done Pascal, Volta, and Turing now. But I think this is only a few years old. This is the architecture that Blue Waters has. But let's look what we're trying to make here. So this is probably, I'm sorry this axis isn't labeled, but this is probably the number of conflicting updates that we're trying to make. And so, scatter without conflicts. Yeah, okay. So yeah, maybe this is the number of outputs, and this has some number of conflicts per output, and this one doesn't. But you can see that in, yeah.
Yeah, so I think the point of these slides was to just show you how the atomics are basically evolving through the architectures.
Yes. So you'll notice that in this extremely old GPU, this was kind of like the first GPU. I think this was maybe the first architecture that supported this CUDA compute. And you can see that the atomics were terrible. Right, so this is atomics. We're using atomics in the scatter implementation, but we've set up the problem so there's no conflicts. So the atomics are relative. There's no serialization even though you do atomics. Does that make sense? But they're still not necessarily as fast as a normal low modified score. But when we introduce some conflicts, this old GPU's atomics get extremely bad. Fermi was better, and since then they've actually gotten even better. And I guess one other point that I want to make is that atomics on shared memory are much, much faster than atomics on global memory. So if you do find that you have to do atomics, if you can find a way to do them atomically in shared memory, and then move all of your results to global memory, just with a store, it might be worth doing. And so I guess part of the reason for this is that this is getting a little bit more into the architecture than I know, but that I know the details of. But on the surface, the atomics happen on modern GPUs in the L2 cache, and I guess this GT200 had no L2 cache. They did the atomics at the level of main memory, which is just much further away than the L2 cache, and so the atomics were slower. So now we're zooming in here so we can actually see, right? So this is way off the top. Right? We zoomed into 6 milliseconds instead of 140. And so you can see that even from Fermi to Kepler and Maxwell, the atomics have gotten a lot better. And so, interestingly, the scatter approach in Kepler and Maxwell is now, so using atomics, like this really easy approach, is as good as all the work that you did to go through the gather approach on the old GPUs. So NVIDIA is working for us a little bit here, making some of these really important operations faster. Okay, and here we just zoomed in even a little bit more. And I'm sorry, I don't really know off the top of my head how much this has changed since then. But I think the big jump, I think there was kind of a jump after Maxwell. I really don't know. Do you know, Simon?
Yeah, so between so Fermi to Kepler, they improved global memory atomics. They added some buffers to the L2 cache. Between Fermi and Kepler, so between Fermi and Kepler, they added improved L2 cache, so global atomics. Between Kepler and Maxwell, they added better shared memory atomics. It used to be done in software, now it's done atomically in it's done in hardware.
Showing up here.
Right, and then the atomics are basically the same right now. They haven't done a big jump, but now they have scopes. So now you can do more complex patterns, but the performance is basically the same.
Right, okay. So what Simon said is that they improved global atomics from Fermi to Kepler, shared memory atomics from Kepler to Maxwell. Since then, the sort of architecture of how the atomics are done has not changed much, but they've changed the flexibility of some of the atomic operations. So you could say, I just want to do this operation atomically within a block, or within a warp, or something like that, as opposed to having it be atomic maybe across the whole grid. So flexibility for the programmer, right? So making it more programmable, essentially. Oh, okay. So Simon said something. So when we're writing CPU code, often when we're thinking about performance, the most important thing is whether we're using the cache effectively, not really whether we're using, like creating, twice as many floating point operations as we need to. That is much less important than whether we're using the cache effectively. And so the input-oriented sequential code, remember that loops over all of the inputs and writes to, that has each output and it loops, the scatter. So the scatter takes every input and writes it to all of the outputs. Oh, right. So yeah, the input-oriented code we take. No, that's gather is where we go through the large data structure for each atom. Yeah, sorry. The input, right? The energy grid is our output. Right, so the input-oriented code, we're taking every input atom and writing to every grid, right, sorry. And so if that output, the energy grid, is very large, by the time we come back around to the beginning for the next atom, it will no longer be present in our cache. So for every atom that we go through, we don't really get to use our cache when we're making these repeated modifications to the output. And so this fast sequential code actually isn't the input-oriented one. It's an optimized output-oriented one where we're repeatedly accessing a smaller array. But in GPUs, we're a little less worried about cache performance, a little more worried about We sort of have the same thing, but we do it explicitly through shared memory. That's how we capture locality in the memory system. Oh, okay. So this is the fast sequential code.
I think the biggest acceleration was for sequential code.
Yeah, yeah. So this is when we're talking about CPUs, and this is the sequential code. Yeah. So here, right, we start by, basically we look at this level, we're only considering a single output grid point, and we loop over all of the atoms. And so when we check all of those atoms, we'll get them into our cache. And then when we move on to the next grid point, hopefully the number of atoms is small, and it will still all be in our cache when we access the next one. When we compute for the next x, all the atoms will still be in the cache. And right, that's kind of makes some sense because right, our grid could be, we could sort of divide this arbitrarily, but you know, maybe there'll only be 1,000 atoms or something, right, that we're really trying to place in this small space. So we compute this at arbitrarily high resolution, make this data structure arbitrarily large. We still have relatively few number of atoms.
Obviously, you also have that it's better to have the output though, because you're going sequentially through the output.
Oh, sure, yeah, sure. So I guess, yeah, and so then to avoid this cost of computing x, y, and z, the distance the atom is from x, y, and z, we can't avoid computing it for x and y, but since we're only considering one z slice at a time, the dz squared for all of these iterations will be the same. So it'll be different for each atom, but it'll be the same for all these iterations. So we'll have an array that's the number of atoms, which is the dz squared, that we can compute ahead of time. So the cost of that is just in the order of the number of atoms. So you need some additional space. And this is kind of a common trade-off where you're trading off compute for space, right? If you don't want to do redundant computation, that essentially means you need to do it ahead of time, which essentially means you need to store it somewhere. So that's a very common trade-off. If you sit down and think about the transformation that you're doing when you're writing code, you'll find that you're making that transformation one way, that trade-off one way or another very, very often when you're optimizing. Okay, so we talked about some of this. So sweeping across we prefer to sweep across a small atom data structure once for each grid point, then prefer to sweep across a large grid data structure once for each atom. Because the atoms will be in our cache, the large grid will not be. And so I guess on this last point, in this class we tend to focus a lot on writing fast parallel code, and we compare it against bad sequential code. We're talking about speedups. And that's very common to do in the literature also. So people will go to heroic lengths, do zany transformations on their code, accept all kinds of trade-offs to get a good GPU speedup. But they could really probably put the same effort into their CPU code, right, and to make a more fair comparison, and they often don't. And there's plenty of tricks you can play on CPUs, right? Modern CPUs have like 40 cores, 8-way SMT, really wide vector units, relatively large amounts of memory bandwidth. You might have multiple sockets. You can play with a lot of different kinds of locality, just like you can on GPUs. But often people don't go to such efforts on the CPU side, although a lot of the it has a similar feel to writing fast GPU code, writing fast vectorized CPU code, worrying about locality. You're thinking about a lot of the same things, a lot of the same transformations, which I guess is kind of made by this point, right? This is also the scatter together transformation of fast CPU. So back to the very beginning, I mentioned the reduction is the sort of degenerate case, right? So the problem is that, right, we have this doubly nested loop, except we only have one output, so really we just loop over all the inputs and add this. But remember, in the gather approach, I said we can only have as much parallelism as we have outputs, right? If we have two threads working on this guy, then we go back to the problem of having contention, right? That we were trying to avoid in the first place. And so, of course, the fix is that this doesn't have to be your only output, right? We can have a tree of outputs, essentially, and have parallelism the whole way down, which is exactly what we do. Oh, this is what I was saying. There's no output parallelism, but the scatter is not good. You wouldn't do this reduction just with atomics. So this privatization is essentially this scatter to gather transformation, but we're creating additional outputs so we can create additional parallelism. Does that make some sense? So it's basically just a sort of a special case of the scatter to gather transformation where we're creating additional outputs that we have additional parallelism. And that's what we have for today. So, yes?
On the GPU, how do you, on the previous example we were doing with the grid, how do you actually run the scatter algorithm without conflicts?
On the
Like here.
oh, no, so the scatter with so probably this is not that example.
Oh.
This is a constructed problem where we're adjusting either the order in which threads update locations or the locations that are affected by each thread to prevent there being conflicts even though we're using atomics. So it's not the same code.
Oh, okay.
Yeah, yeah. This is a constructed example just to create these plots. So there's playing some tricks with the indexing to control whether there's conflicts or not, and how many conflicts there are. Good question. Just a toy example. So right, if you're not enrolled or recently enrolled and you don't have access to things that you want, I'll just put my net ID up here again one more time. Email me. I guess we'll be trying to figure out that. Does that interfaces nil problem? Have you tried only on one, like your own system, and that's it? So yeah, because I know it's not happening to everyone. So maybe we can try to figure out what exactly the problem
I
is.
think I downloaded like a different version of Rod.
That's possible.
I downloaded it from like Rod courses.
Oh, okay. Yeah. So we built special binaries for this class. So you really do want to download it from this README on the GPU algorithms lab. Yeah. Because you'll notice that this URL goes to my Dropbox and not onto the Roddy GitHub. So try that. I hope that works for you. I'm not optimistic, but definitely start here. And then if that still doesn't work, we'll figure it out and see what else. But right, try it on EWS if you're really just stuck. I know it's a little bit inconvenient. Okay? Otherwise, yeah?
You said you're part of doing that, but
I don't know if I can explain it. So is this? So let's talk about this. So Wednesday will be back. Is this next Thursday? Okay. So I don't know exactly what form that takes. And since we don't know that, maybe I'll talk to them about not surprising everyone with that. Yeah. That's a good question.